Hello! In this video, we're going to prove the following theorem. For every positive integer n, 3 plus the square root of 5 to the power of n plus 3 minus the square root of 5 to the power of n is an even integer, and it's positive. So, let's first do some scratch work to see how we could prove this. Let's first try to prove this by induction. For the base case, we would want to show that this is true in the case where n is equal to 1, but that should be pretty easy, right? Substituting n for 1, you would get 3 plus square root of 5 plus 3 minus the square root of 5. That's just equal to 6, and 6 is an even positive integer, so we're done. We're more concerned with the induction step, right? For the induction step, we let k be an arbitrary positive integer and assume that this is true for k. So our induction step is assuming that this quantity is an even positive integer. So in that case, it's equal to 2p for some positive integer p. The whole goal is to show that this guy, where instead we have k plus 1, is also an even positive integer. So let's write this out, where instead of k, we have k plus 1. We're trying to show that this quantity is an even positive integer. And to do that, let's rewrite this guy as 3 plus square root of 5 to the power of k times 3 plus square root of 5. And similarly, for this guy, let's rewrite it as 3 minus square root of 5 to the power of k times 3 minus square root of 5. Now we're going to try to bring this quantity into our work. And to see how we can do that, well, let's distribute this quantity across this parentheses. So we're going to get 3 times this guy plus square root of 5 times this guy. Right? So we get that. And as for this guy, let's distribute this guy across this parentheses. So then in that case, we would get 3 times this guy minus square root of 5 times this guy. Right? And then we could group together the terms that have 3 in it, group together the terms that have square root of 5 in it. So as for the terms that have 3 in it, we'll factor out the 3. And as for the terms that have square root of 5 in it, we'll factor out the square root of 5. So we get this. Now, as you can see, we have brought this quantity into our work. And this guy is equal to 2p, so let's just substitute it for 2p. So we're left with this. So then, remember, we're trying to show that this quantity is an even positive integer. So then, how can we deal with what we have here? How can we deal with 3 plus square root of 5 to the power of k minus 3 minus square root of 5 to the power of k? Now, the way that I saw how to deal with this is by observing that this is in the form a to the k minus b to the k. And in general, we can write this as follows. We can write it as this. So notice, the first factor is really just the difference between a and b. So if we write this guy in this form, the first factor is going to be the difference 3 plus square root of 5 minus 3 minus square root of 5. And so if we actually perform that, what's that equal to? This is just equal to 2 times the square root of 5. So if we re-express this guy in this form, it's going to be 2 square root of 5 times some other quantity. But notice, we would be doing square root of 5 times square root of 5. So the radical would go away. And we'd be left with 2 times 5 times this quantity. Well, if this quantity was an integer, then this would become 6p plus 2 times 5 times some integer. So this would be an even integer, which is what we need, right? That, in fact, the claim is that this is a positive integer. So we'd have an even positive integer, which is what we need. Okay, so then how do we show that? Well, the idea is we're trying to show this quantity is of the form 2 square root of 5 times some positive integer. And so we're going to prove that as part of our induction argument. So we're going to modify the statement that we are proving slightly. We're going to prove for every positive integer n, this is true, and this is true. So we're going to prove by induction for every positive integer n, this is true and this is true. Because if we prove this, it follows that the original statement we are trying to prove is true. So, to prove this by induction, well, in the base case, we would establish that this is true for n equals 1, which we already know happens, and we would establish that this is true for n equals 1. In fact, if n is equal to 1, this just becomes 2 square root of 5 times 1. So just take q to be 1 and you're all good. So yeah, the base case is good. For the induction step, we are working with an arbitrary positive integer k, and we assume that this quantity is an even positive integer, and we're assuming this quantity, where n is equal to k, has this form. Right, so we're assuming it has this form. So, then in that case, we can rewrite this guy as 2 square root of 5 times q. But then this is just, this I'll write right here. This is 6p plus 10q, and we could factor out a 2, so this is just 3p plus 5q. So this is an even positive integer. This is not correct. So this chain of equality shows that this quantity is an even positive integer. So we're all good here. But we also need to establish that 3 plus square root of 5 to the power of k plus 1 minus 3 minus square root of 5 to the power of k plus 1 has this form. Right? We need to establish that as well. And again, we're going to re-express these two guys in the same way that we did right here. Again, we're going to distribute this guy across the parentheses. As for this guy, we have a minus sign here. So you got to keep track of that, but distributing this guy across the parentheses, we get this. So then, once again, we group the terms that have 3 in it, factor out the 3, group the terms that have square root of 5 in it, factor out the square root of 5. So we get this. So then we substitute this guy for 2 square root of 5q. And as for the next guy, we substitute this guy for 2p. So we get this. So then, as you can see, both terms have 2 square root of 5 in it. So factoring out the 2 square root of 5, this is 3q, this is p. And so it fits the form, right? 3q plus p is a positive integer, so it fits this form. So we're good. We have a proof. So the idea is to prove the original statement we're trying to prove, which is for every positive integer n, this is true. It suffices to prove for every positive integer n, this is true and this is true. So that's the idea. So let's get into the proof. So to prove the original statement we're trying to prove, it suffices to prove for every positive integer n, this and this are true. So we're going to prove this by induction. So we'll start off with the base case. The base case, we're working with n equal to 1. And let's just take this expression, substitute n with 1. Well then, we know that the square root of 5s are going to cancel out. 3 plus 3 will give us 6. Right? And 6 can be written as 2 times 3, which fits this form. Right? Just take p to be 3. So we're good there. Next, we got to show that this is true for n equal to 1. Well, substituting n for 1, what we get? We get this, but we see that the 3's cancel out. We're going to be left with 2 square root of 5 in this case, or 2 square root of 5 times 1. So just take q to be 1, and we're good. So this completes the base case, right? We have proven that these two things are true in the case where n is equal to 1. So this completes the base case. Now let's move on to the induction step. In the induction step, let's give ourselves an arbitrary positive integer k. And we assume, for our arbitrary positive integer k, that this and this are true. So, where we take n to be k. The whole goal of the induction step is to establish this for k plus 1. Right? We want to show that this guy to the power of k plus 1 plus this guy to the power of k plus 1 is equal to 2 times some positive integer. And we want to show that this guy to the power of k plus 1 minus this guy to the power of k plus 1 is equal to 2 radical 5 times some positive integer. If we prove that, that will complete the induction step. So, let's write this guy where instead of k we have k plus 1. And what we're going to do is we're going to pretty much follow what we did in our scratch work. Right? So then we'll just substitute this quantity for 2p, substitute this guy for 2 radical 5q. So then this is 6p, this is 10q, and from here we just factor out a 2. So then this becomes 3p plus 5q. And so this demonstrates that this quantity is equal to 2 times some positive integer. So that's it. Next, let's do the same thing for this guy, where instead of k we have k plus 1. We're going to show it's equal to 2 radical 5 times some positive integer. Again, we're going to follow what we did in our scratch work. So we're at this point, but then we substitute this guy for 2 radical 5q, and substitute this guy for 2p. So then in this case, this is 6 radical 5q, or actually, we just factor out the 2 radical 5 right away, right? This is 2 radical 5 times 3q plus p. And that's it. Right? This is 2 radical 5 times some positive integer. So, this completes the induction step. So, let's just say, because we completed both the base case and the induction step, let's just say this closes the induction. So, the desired statement is proven. Right? That is, we have proven for every positive integer n, this statement is true. But that's enough to say that this statement is true, right? Because if we give ourselves an arbitrary positive integer n, we know that this quantity, basically we know this quantity is equal to 2p for some positive integer p, and therefore it's positive integer and it's even. So that's it. This completes the proof. And so yeah, that's pretty much it for this video.